Hello, everybody, and welcome to the Big Bear Math Channel. And we have got a huge bear to try to tackle together today. Today, we're going to look at the difference quotient. And as you're beginning your journey to becoming an elite calculus student, this is going to be a monster concept. And the deeper your understanding is of this concept, the more that's going to fuel your understanding throughout the entire course. And this is going to play a huge role as we start to create our definition of the derivative, as we shoot towards this idea of measuring the instantaneous rate of change of a function. So real quick visual, let's open up with this idea right here. I've got this function in red, okay? And I'm just walking along this curve. We're walking and we're walking and we're walking. And then all of a sudden we say, bam, right here at this moment, freeze. And our goal is to measure our instantaneous slope at that particular moment in time. And you'll notice like every point on this curve has its own unique slope. So this point right here has a slope that no other point on this particular curve has. And so to try to measure that instantaneous slope, we're going to introduce what's called a tangent line. Bang, magic. And so this helps us. The slope of this blue line is equivalent to the instantaneous slope of that red line. But the challenge is right now, the slope formula that we've relied on, throughout our math career up to this point requires 2 points. And so what we're going to do is we're going to introduce what's called a secant line. And clearly these two lines do not have the same slope now. But what we're going to do is we're going to take this point right here and we're going to just slide it, or float it along the curve so that it gets closer and closer and closer to that point that we were most interested in at the beginning of the problem. So let's hit the play button and watch this unfold. Okay. It's getting closer and closer and closer and closer. And you'll notice the slope of that purple line is getting closer and closer to the slope of that blue line until there's this magical moment, boom, this magical moment when the purple dot sits right on that blue dot and that purple line is sitting right on the blue line, and they do actually share the same slope. So that's kind of just a real quick visual of what we're going to try to explain more analytically here in a moment. A little terminology as we go forward. This is my fixed point right here. This is the point that I'm trying to find the instantaneous slope of. This point up here, we're going to call that our floating point or our movable point. So we come back over here, and so up to this point in our math career, our slope formula that we're really comfortable with has always measured the slope between 2 points, emphasis on 2. And hence it's measured what we call average rate of change. It was always defined as rise over run, change in y over the change in x. And there was a couple different ways that you could say that. So let's see, as we get into this picture right here, let's see if we can mark this up a little bit. Here was our first point. This would be my x sub 1, and here's my y sub 1. Here's my second point. This would be my x sub 2, and this would be my y sub 2. Okay. Or conversely, we could say, okay, this point right here, here's my a, here's my f of a. Or for this point here, here's my b value, and this is my f of b value. All right. So, all right, let's see. But we don't always have 2 points there, the luxury of 2 points per se. So our new goal is to measure the slope at 1 point, and hence measure what's called not the average, but the instantaneous rate of change. So now we've got this, we'll say this particular point right here where my crosshairs is sitting is where the blue line intersects the red curve, and the instantaneous slope of the red curve is, at this particular moment anyway, is equivalent to the slope of that blue line. So what we're going to do is we're going to use something called the difference quotient. And if you haven't seen this before, we're going to try to explain where this comes from. And there's a couple different versions of it. In fact, these are the two most popular. This is probably by far the most popular from my experience. This one's also very good. There's some other variations out there. And in fact, there are many different varieties of the difference quotient, but here are the common theme no matter which variety you see. There's going to be what we call a fixed point. There's going to be what we call a floating point. And hopefully you've already, dealt with the limits here. Why is there a limit sitting in the front of that fraction? Well, the limit process is what moves that floating point closer and closer and closer to that fixed point until we get to that magical moment where they coincide perfectly. Okay, so that most traditional one that we mentioned earlier that had the f of x sub 1 plus h minus f of x sub 1, etc. I want you to think of that h as measuring the gap between the 2 points. And we'll go back to our Desmos screen and try to articulate all of this. But h measures the gap between the 2 points. The first point is my fixed point, and that is the point where we were trying to find the instantaneous slope of. The second point is just a movable or floating point that we're going to drag closer and closer and closer to that fixed point. As I do that, what's happening to the gap between the 2 points? Okay. Again, if h measures that horizontal gap between them, that gap is going to get what? Bigger or smaller? Yeah, it's going to get smaller. So we'd say hence the value of h is shrinking. And of course, in theory, we're going to continue to drag that floating point until it sits right on top of that fixed point. And at that particular moment, here's the magic. At that particular moment, the value of h becomes 0. Okay? So let's go take a look at, one last comment here before I leave this page. This, believe it or not, and we'll show you how this is our slope formula. This measures average rate of change. But once I introduce the limit and put the limit or attach the limit to that front end of that fraction, it becomes instantaneous rate of change. I'm going to try to convince you why as we go back to our Desmos screen. Okay. All right. Let's see if we can cook this bear up. So at this particular moment, all right. So this bear right here, we'll call this x sub 1. And then this corresponding y value would be f of x sub 1. All right. Now what we've done is we've picked a second random point. I want to stress that this point up here is purely random right now. And this point is, let's see, well, it was x sub 1 units to get me there. And then from there, we're going to move forward an additional h units. So that's why we like to say h is the gap between the 2 points. So this new point right here is all of h or x sub 1 plus the h value. So adding this distance to this distance gives me that x coordinate. And then this is going to get a little goofy looking, but this corresponding y coordinate would now be f of x sub 1 plus h. So let's say I wanted to measure the slope of this purple line right here. Okay. I'm going to employ my slope formula, and we're going to say we've got this y coordinate right here, f of x sub 1 plus h, minus the other y coordinate, f of x sub 1, divided by, now we need to measure the run, so it's going to be this x coordinate minus this x coordinate, x sub 1 plus h minus x sub 1. Now you'll notice a key opportunity to simplify this expression. This term will cancel with this term because of the subtraction. So as I simplify it down, I've got f of x sub 1 plus h minus f of x sub 1 all over h. All right, so a lot of people, this will be your difference quotient right here. Finish that x. But we're not content with just measuring the slope of that purple line. We said, let's see, let's hit play here. We said we wanted to move the floating point closer and closer and closer until that purple point sits right on top of, bang, right there. So what we've done is we've shrunk the gap. And as that point was moving, as that little video clip was playing, h was shrinking. So all we're going to do is we're going to get real magical here. And we're going to attach a limit here. We want to find the limit as h approaches 0. We want that gap to become non-existent. And ladies and gentlemen, once that happens, you've got a formula for measuring instantaneous rate of change, instantaneous slope, that we're going to affectionately refer to as the derivative. And so we're going to say the derivative, that's the little prime sign we attach to f, at the point x sub 1 is equal to this expression. So we're not going to evaluate any specific examples today. We just wanted to develop that concept and create that visualization in your mind of some floating point moving closer and closer to a fixed point that we're trying to find the slope of. Ladies and gentlemen, I hope that helps. If that helps, if you like this video at all, please subscribe to our channel below, add some comments, and help us fix and improve this video going forward. Thanks a lot. Have a great night.